So, to explain dielectric elastomers in a nutshell, let's start by looking at a block of rubber with no modifications. Rubber, similar to liquid water, is incompressible, meaning that volume remains constant when it is deformed. So if you apply a pressure to the top and bottom of this rubber block, it will deform in the x and y directions. Think about squeezing a balloon. When you squeeze it, it bows out in the directions it's not being squeezed in, right? So, when you shorten the height of this block, the depth and the width will expand in order to keep the volume constant. So how do we apply a constant even pressure over the top of this rubber block? Well, one way would be to attach a conductive material to the top and bottom of the block. We need to keep in mind, though, that this material needs to be flexible so that when the block expands, the conductor expands as well. An excellent conductor for this is carbon grease. When these conductors are charged, theoretically, the rubber block will become a parallel plate capacitor. And if charge is allowed to build up, it will cause the two conductive plates to pull towards each other. This will cause the rubber to compress in one direction and expand in the other two. This means that the stretch of the rubber is now controllable by the voltage applied to the top and bottom of the DEA. Additionally, as we stated earlier, this essentially acts as a parallel plate capacitor. The capacitance, though, is a function of both area A and thickness D. This means that the capacitance changes as the DEA is deformed. This capacitance can be measured, and when the DEA is deformed, then you know that the elastomer is in its deformed state. Here we see the area in the unstretched rubber block, as well as its thickness. On the right side, we have the area in the stretched rubber block, as well as its thickness. From this graphic, you can see that the capacitance will change by a significant amount depending on the stretch. So, not only can DEAs be used as actuators, but they can be used as strain sensors as well. Now that we've gone over some of the basics of DEAs, we're going to show you some examples of what you can make and what materials you will need to do so.
Here are some of the things that you may need in order to make your own DEAs. First, you need a cutting board to cut these plastic in precise shapes. This can also be done in a laser cutter for more precision. You may also need a thin plastic sheet. Now, this can be recycled from a strawberry package or any other plastic package you may find. As stated before, you will also need carbon grease, gloves to avoid spreading the carbon grease, copper tape as an interlay between the carbon grease and the power source, in this case an alligator clip.
Pre-stretch your VHB onto the acrylic ring by a preset amount. In this case, we're stretching by 3 times.
Plain carbon grease on both sides, making sure to cover the entire electrode area.
Attach copper tape to both sides to create a link between your voltage source and your actuator.
Paint a line of carbon grease from your electrode to the copper tape.
Measure your capacitance with an LCR meter and compare it with your calculated value.
Clip electrodes to your copper tape leads.
Before turning on the amplifier, set up your function generator. When you're ready, turn the power on.
At 7 kV, maximum aerial expansion achieved is 50%.
Loss of tension is an instability that occurs at large area expansion.
At high voltage, or in this case frequency, the actuator will break down.
Different shapes could give interesting actuations. Now, let's make some flapping actuators. These are the materials you need for the flapper. Thin plastic, tools for cutting, thicker plastic for the frame, super glue to glue the plastics together, VHB tape, and copper tape.
Assembly is the same as with the previous actuator. Apply grease to both sides.
When high voltage is applied, the actuator flaps. It creates sound at higher frequencies.
Now let's have some fun with DEAs.
Oh, it's burning actually. Sparking and burning at the ends.
To the common folk, this looks like a regular swan here. But if you looked underneath the hood, it's a super powered swan. Cool.
Yeah. Yeah, and that's 10, that's 20, 30.
20 is the best, yeah. Alright, I think what we're gonna need now. Alright, let's kill it. Turn off.
No, put him on that bike. There's a motorcycle. Is there a motor?
Oh lord, I feel like it's gonna have mechanical failure before a dielectric breakdown.
Yeah, it's just gonna rip it in half.
I mean, Chad, why are you doing sit-ups in the middle of the lab?
7 o'clock, time to get my swole on.